Hello and welcome to Toddcast number 39. So this was in a block of Toddcast 33 through 39. In 33, we covered the introduction into SN1, SN2, or just substitution in general, and alluded to that. 34 and 35, we did SN2 and SN1 respectively. 36, we did a comparison of conditions that would do one reaction versus another. 37 and 38, we introduced elimination, E1 and E2. So 39 puts everything together. We can consider all the reactions because they're done under very similar conditions. It's usually very small nuances that distinguish what the major product will be. And reality is, whenever you have elimination, there is the high probability you'll get a small amount of substitution. When you do substitution, there are conditions where you could potentially get a notable amount of elimination product. So we always have to maximize which is the most favorable reaction, and therefore the major product we're going to get from all this. Okay, so with that in mind, I want to go ahead and start by just looking at a ton of reactions. And so early on, want you to start identifying what the compound is over the arrow and what kind of substitution you have. So we have, for the very first one, the upper left one, we have a tertiary electrophile. That's key. So I know that eliminates the possibility of an SN2 reaction. Um, and an SN1 is still possible. The chlorine could leave and that group could come in, but that's a really strong base. And as a consequence, we're probably looking at elimination. We saw earlier that ethoxide's kind of a medium-sized base. So it's going to have some Hoffman, some Zaitsev. It was about 2/3 Zaitsev when done at 25 degrees Celsius. So we don't have a temperature there. So I'm just going to go on the assumption then is that it favored the Zaitsev. So this would lead to the Hoffman. This would be Zaitsev and this be Zaitsev. So we have our alpha right here. We have beta here. We have beta here and beta here. But this time we have two betas here and only one there. So it's going to favor it by also just the greater abundance of H's to choose from. So medium base, medium size base. So a medium sized strong base, it's HF product. Could have also drawn the double bond on this other side. Same thing, same compound. Okay, so moving down, now we're using a much larger base, hefty Hoffy. So I got to go with Hoffman elimination. So instead of going on the inside of the ring, it's now going to have to go to the top of the ring. So that's your Hoffman elimination. So medium or small leads to Zaitsev. Small definitely Zaitsev. Medium, predominantly Zaitsev with some Hoffman. And then large base, Hoffman. LDA, if this is your first time seeing it, we actually drew it as one of the bases to remember. So I'll draw it out. It's lithium. So let me go ahead and put the negative here and positive here. So lithium's the counterion. So lithium diisopropyl amine. So it is a bulky, strong base. So it's about as large and strong as they get. So just like this one, large base, it's going to result in Hoffman elimination. So this is Cl as a leading group. So here's my alpha. It could go beta on that side or beta on this side. It's going to go beta on this side because that bulky base is going to choose the less hindered. Again, we're back up here now to a medium-sized base again. So medium, we're going to end up getting this elimination, Zaitsev. Want to use LDA, bulky base, just like we had down here. So LDA is going to have to go to the less hindered, so you're going to end up with this. So if we use NaCOH3, again, I think I want to get right here because I have my beta here, my alpha, my beta. What the heck happened? it didn't do what we expected. So this is one of those I want you to pay extra careful attention to. If I consider the H's on two beta positions, this CL is in front. It has the anti because it is an E2 product. Hoffman and Zaitsev are both the result. Well, I guess Zaitsev could be the result of an E1 as well. But in this case, we're using base. So it's got to be an E2. E2 has the anti. It ends up this H and that CL are on the same side. They can't get eliminated. You cannot get double bond forming on that side. So you just got nailed by a trick question. It is the popular and ever so fun non-anti-beta hydrogen trick. Well, it's a lot of words in a name like that. But professors of OChem love to throw this trick question where you cannot get elimination, where you think you should, because the H can't rotate. No matter what we do, that H cannot be anti. If this is equatorial up, this would be axial up. If this is axial down, this is, or I mean, sorry, if this equatorial down, this would be, wouldn't be down. If this equatorial, this would be axial. If this is axial, this would be equatorial, no matter what you end up doing, because they're both up in adjacent positions. You can only get elimination if it's axial up and axial down. So it can only be anti if one's up and one's down. So here's a more clear vision of that. The leading group has the anti in order for the double bond to form. So if I have this structure here, may not be the ideal, most stable conformation, but that's a thing that you have to also keep in mind. The most stable conformation is one we think should exist, but it's actually the most unstable one that sometimes is the key one because if it's less stable, it's more reactive. So we do this a little bit in OChem. You'll see this all the time in biochem, where the active site conformation of an enzyme is oftentimes an unstable position, which means it'll react very quickly and try to contort back to something stable, which will kick out the product. So same thing here. This is not the most stable conformation, chair conformation, but it is the only one that can react. So this BR, it forms the double bond here because, just like that previous example, this BR is down and CH3 is up. So the CH3 is up, the H must be down, down in equatorial, down in axial. They're not anti, cannot be eliminated there. You can't get the Zaitsev. On this one, you have two H's. You have the equatorial, which is useless to me, and you have the axial. So the axial and the axial are the ones that are anti to one another. So they'll get eliminated. Okay, so this is that same trick, but done with a chair conformation. Okay, we can also look at it from the Newman projection perspective. So this is my leading group, the chlorine. It is anti to a CH3, so it cannot get elimination. Here, it can get elimination. So this is already lined up to react. This one has to rotate to get in the right orientation. So let me get rid of my circles and say that the H that it's going to eliminate is right there. Whereas the H this is going to eliminate is anti. So my 2R, 3R as opposed to 2S, 3R compound. So the 2R, 3R is fine. The 2S, 3R has a rotate. So I'm going to try to emphasize this by rotating this into the up position, which moves that there and moves that over here. Move the H down, which causes that one to go up there and that one to go over there. So when you rotate, again, I rotated this 60 degrees up to this position, which meant this one had to go 60 down to here. This had to go 60 over here. And then back, I rotated this H down to here. So it ended up here, which means that CH3 had to go here. That ethyl had to go over here. So you rotate it so that you now have the two groups 180 or anti to one another. The double bond's going to form right in this spot here, which means that my ethyl and methyl are going to be on the same side. They'll be cis or Z to one another. H and CH3 will be cis to one another. Over here, I rotated just to be complete, but really all we did, we just took this entire thing and rotated. So we just basically turned everything by 60 degrees. So now we have the H and the ethyl on the same side and the two methyls on the same side. So when you undergo elimination, again, these two are opposite, these two are opposite, and these two are the same. These two are the same. This one, ethyl is going to be on the same side as the H, two CH3s. This is Z because the larger of the two, ethyl over methyl, and methyl over H on the same side. They're on the same side. So there's this. And on this one down here, both of your groups are on opposite sides. So it is E. The stereochemistry becomes key. You have to make sure you can recognize that. Drawing the mechanisms, this is where we're going to transition into the big picture. So we're kind of done messing with the elimination. Now I want to see the big picture. So I have O-mess, which was an OH that got methylated. So this is a really good leaving group. So the leaving group is going to first leave. And when it does, it's going to leave a carbocation. This is a secondary carbocation because there's 1, 2 carbons. Up here, there's no H to migrate over, but there isn't always an H. H is ideal. You want to move an H around, but if there's no H, then you settle for the next best thing, and that is the next lightest thing to move, which would be a methyl group. In this case, the methyl is going to move over. So rather than a hydride shift, an H moving over, we're going to have an alkyl shift. So alkyl group is going to move over. Now we have a tertiary carbocation. And from this point, two things can happen. Tertiary with a carbocation, so it could be an SN1 where it comes in, or this can act like a base and pull off the H here and kick in. When the H is on a beta carbon next to an alpha carbocation where the group is left, it ends up this H becomes significantly more acidic, and this is a strong enough base to pull it off. So these lone pairs can pull that H, those electrons go in here, and you end up with that double bond. So you could get an E1 reaction on this tertiary. Okay, makes sense. A protic solvent, a protic solvent, excuse me. So makes sense it'd be a 1, and elimination is one possibility. But you can also get substitution as well. So we're going to have something sort of similar. I is going to leave. So instead of the O mass or O toss that left in the previous one, we have I leave. Now we have H to move over. So H being the lightest is the easier thing to migrate. You're going to move an H rather than a CH3. If the H moves over, again, it goes from a secondary carbocation to a tertiary carbocation. So we've improved our lot. And now instead of elimination, you can have nucleophile come in. The nucleophile, as mentioned here, could come in from the backside or the front side equally. Because it's a symmetric molecule, it doesn't matter, but you have to consider the stereochemistry. So if there was a chiral center here, then it would matter. So this is going to come in as a nucleophile. It's now protonated, so you're going to have to lose that H. So the I minus maybe will be strong enough, but probably it's going to have to just combine with another ethanol. So ethanol is going to come in, take the H, and leave this compound in solution, and this is our product. Meaning, we just got a case where this underwent substitution. The example before, the exact same molecule underwent elimination. When you have a mechanism question on an exam, draw the mechanism that leads to the product they list. Whether you think it's most favorable or least favorable, is irrelevant. You draw the mechanism that leads to the product that was given. So the previous example, same reagents, essentially similar, well, uh, same ethanol, essentially the same carbon-based electrophile, um, CH3 next to some leaving group. Not exactly the same, close enough. But that one was elimination because it showed a double bond. This one, substitution, because it shows one group leaving and a new one coming in, but on a next carbon over. You will no doubt, I don't care whose class you take, mine or anybody else's, you will have to show knowledge of a mechanism that involves rearrangement. This is just par for this course. Okay, so putting it all together, information overload. A lot is coming at you, and so you need to have a strategy. So the plan is we're going to identify the electrophile first, the other reagent, be it a nucleophile or base second, and then the solvent conditions and temperature last. So if you have primary, secondary, and tertiary, those are different types. Primary, I'm going to put all the options here, SN2, SN1, E2, E1, SN2, E2, SN1, E1, etc. So these are for primary, these are the ones for secondary, these are the options. If it's primary, I know I can't get a carbocation, so that gets rid of the E1 and SN1. They're gone. Secondary, you're pretty much open to anything you want. In tertiary, the twos are going to be gone. Or the SN2, I should say, it's going to be gone. Can't have that group come in. It's just too crowded. Elimination is still possible. Okay, so next on the agenda, consider the other reagent. So it's either going to be a primary with a base or nucleophile, secondary with a nucleophile or base, tertiary with a nucleophile or base. So if it acts like a base, acts like a nucleophile with a primary, acts like a nucleophile or base, secondary, acts like a nucleophile or base with a tertiary. So again, let's update. We have E2 and E2 and SN2 as the options here and here. We have, let's see, all of them are still possible for this. Didn't get rid of anything. And we have E2, E1, and SN1 possible. So we now have 6 combinations we're looking at. Primary with a base, primary with nucleophile, secondary with a nucleophile, secondary with a base, tertiary with nucleophile, tertiary with a base. Okay, if it's a base, you favor elimination. Okay, if it's a nucleophile, then you favor SN2. We're done. So primary, pretty easy. It's primary, SN2 or E2. If acting like a base, elimination, act like a nucleophile, SN2. There is a possibility of getting, let's say, 90% of this and 10% of this, or 87 and 13 or something like that. So we're talking about the major product. If it's a base, the major product is E2, but not 100% product. If it's a nucleophile, the major product SN2, but not 100% necessarily. Okay, for secondary, that's where things get a little bit trickier. So if it's a nucleophile, it can be substitution. If it's a base, it can be E2. Acid would end up being E1 under conditions like that. So I've sort of ignored that possibility of an acid. So acid here wouldn't matter because it wasn't going to be an E1 anyway, but I should have a third column, potentially acid. If it's acid, I do an E1. But we're set for now. In this case, tertiary, E1 versus SN1, nucleophile substitution. Base, definitely going to be elimination, you E2. So this one, I'm not 100% sure what it's going to be because it doesn't depend on the nucleophile. Okay, so last, the reaction condition. This is where you're going to make the hard decision here and the hard decision here. So aprotic and polar versus polar and protic, acidic and protic. So those conditions that kick in. So if it is polar aprotic, SN2, if it's polar protic, SN1. So for this one, we can just go ahead and get rid of SN1, pick SN2. This one, we can get rid of SN2 and pick SN1. For acidic conditions, you end up with elimination. And protic conditions, you end up with SN1. But you still are going to, again, get potential impurities. But this is a pretty good flowchart. Identify primary, secondary, tertiary, then identify nucleophile base, and last but not least, polar aprotic versus polar protic if it's substitution, acidic versus protic if it is elimination. Okay, lots of information. You are ready to do lots and lots of questions on this. So, okay, thank you for joining. It was a wonderful experience, and hopefully you got a lot out of it. So, see you in the next podcast. Bye.